All right. Hi. Welcome. Welcome back from the world of linear algebra, I suppose. The ones who made it, which I see is not everyone. It's easy to get lost on the way. Yeah, and I should say so. Like announced on Piazza, so I made the lab this week a little shorter, but like it's not as if we could stop teaching anytime there is 2 midterms a week, because that would mean that we would never teach at all, basically. So that would also be a problem. Anyway, so for the rest of the semester, what we're going to be doing is kind of more specialized algorithms and data structures, as opposed to what we've been doing up to now, which is kind of a mix of like, sometimes here's an interesting problem, but a lot of the time, like here are the tools in Python and in C that you will need to solve any problem. And one way to look at it is we're going to be looking at, I put it as techniques that have been proven effective at solving computational problems across several domains, so like really useful stuff. The more cynical way to look at it is there is a whole wide world of really difficult computational problems, and computer scientists just know how to solve like a tiny slice of them. And we're just kind of, just looking under the lamp, as it were, for things where we know how to solve them. So here are kind of examples of the kinds of things I'm talking about, and some of them will actually come back to later on this semester. So here are things which are really difficult to do, and nobody really knows how to do them effectively. None of those things have been done, right? So we technically don't know whether black or white would win in chess with perfect play, which is don't. Now, this one, we know how to do it, right? You just run a really powerful computer for a really long time, it'll figure it out. It's just that nobody's gotten around to doing it because the computer is like too expensive and it needs to run for too long for anyone to bother. But like, we know how to do it. Find the proof of Fermat's last theorem. So if you remember Fermat's last theorem, this was like, does x to the n plus y to the n equals z to the n? Does that have solutions for n larger than 3? And the answer is, well, there is a proof that says that no, there isn't. And as you saw, well, like if there was, you could just find it again in the same way that you would find eventually whether black or white wins in chess, if you just try all the possible variants. In terms of finding a proof for a negative, that's a little bit trickier. In principle, again, you could imagine just trying every possible proof and having the computers check every time, like, is this random string that they generated, does it happen to be a proof of Fermat's last theorem? And kind of, that's actually feasible to do in principle, like checking whether a string is like well formatted. That's being done all the time. You can check whether a string is like valid C code or valid Python code. And if you encode how to write proofs, you can do it. enumerating all the possible strings. Many of you have done it on the midterm last week. By the way, you should hear back about it by the end of Saturday, hopefully. That's the deadline for the TAs. So that's in principle possible. It's just that, just like with determining whether black or white will win at chess, because the proof of Fermat's theorem is actually like thousands and thousands of pages, enumerating all the possible strings that would take up thousands of pages, that would take a very long time. So again, people haven't even tried doing it. Sorry, guys. So even doing that, like even trying to do that, like seems pointless. In principle, it could be that there is like a very short proof. Sometimes people discover very short proofs after the fact. It's possible that there is like a 10,000 character proof. You can't really enumerate all the strings of length 10,000 either. There's too many. And how many? Well, you know, just with English, like 32 to the power of 10,000. That's how many. That's a lot. All right. Predict the weather on this day 2 years from now. Again, in principle, we kind of know how to do it, right? We know how to predict the weather for tomorrow pretty accurately. So like just, you know, do the same thing, but more so. In principle, it's possible. Again, not actually computationally feasible, believed to be intractable in general. So it's believed that in the same way that trying to enumerate like so many strings, that there is too many of them, is just impossible. You kind of have to do something kind of like this in order to predict the weather, and it just doesn't scale. Something closer to home, finding the optimal timetable or like the optimal midterm schedule for ANSI 1S. Sounds doable. Obviously, people haven't done it. And why not? Well, because it sounds doable, but it's actually, again, really difficult, because the only way that people know how to find, of course, you have to define what optimal means as well. But apart from that, even if you have defined what it means to be kind of an optimal timetable for the midterms, like imagine that you just say, well, like I want it like as uniform as possible while respecting, the constraints of the profs and so on, right? Even if you define it like that, the only way that people know how to solve this kind of problem exactly is to, again, try every possible arrangement. And again, you run into this problem of it's going to take too long. The timetable for ANSI, we just do manually, to be honest. And like then we negotiate after the fact. That is how I got negotiated into not having major deadlines at all before reading week. Weak person. For like the timetable, there is a computer program that for the lectures and stuff that tries to optimize, but again, you cannot actually find, even for any reasonable definition, it's not computation. Well, like, probably it is computationally feasible, but like not on a laptop to find like the actual optimal schedule. What are things that are possible to do? So, you know, Google can find like, you know, relevant pages to a query on the internet pretty fast. So that's solvable. We'll talk about Google's algorithm actually, hopefully in a few weeks. Generate all passwords of length 7. You've done it. Find a pretty good timetable that maybe not exactly the optimal one, but like a pretty good solution that distributes things pretty evenly. Clearly possible. You can even do it by hand, and you can do it with an algorithm as well. Right. So what we're going to be focusing on is basically like, what are the techniques where it looks at first like it's those kinds of completely intractable problems, but as it happens, you can do it. So, okay, so that's kind of the overall plan. In terms of Python or C, so as you've noticed, we started Python again last week, and part of it is that, you know, there's stuff that I just didn't teach in 180 that's actually important to know, and part of it is that prototyping in Python is just so much easier than kind of doing it in C straight away. I think there's trade-offs. Some people would say I just prefer to write in C, and that might work better for them. I think on average, prototyping in Python is probably easier. Certainly teaching in Python is easier because you don't have to think at the same time about how do I implement it with pointers and how do I also actually like arrange the algorithm so that it works. So as much as possible, we want to kind of separate things out and do the algorithm separately and then the actually efficient implementation separately. With that said, with a lot of the stuff that we're going to be doing, there's kind of no point to doing it in Python, perhaps because it was already done in Python. And what we're doing is we're kind of saying, this is how you would make Python if you had to do it from scratch, or if you had to do a better version of Python or something like that. So that's kind of to do with, you know, the linked lists from earlier this week, for example. And sometimes it's just that, you know, like if you are at the edge of what's possible, like you really actually want to solve chess, meaning figure out whether white wins or black can force a draw, or for all we know, black could be winning initially. That seems unlikely, but it could be possible. Then, well, yeah, like you probably want to write it in C because like you write in Python and you pay like a factor of 2 or 3 or something in terms of speed, usually on average. It depends on the situation. So in class, I'm mostly going to be writing in Python. In the lab, it's going to be like a mix of Python and C. Project 2 is going to be still in C. So ESC190 is like mostly C. But we're using Python basically to make algorithms more accessible and also kind of teaching a few more features in Python. So, all right. So today's going to be dynamic programming. I should mention that I am jumping around a little bit. So this seems like a break from the linked list stuff. And that's because it is. And that's just because dynamic programming is needed for project 2. So it's not much of a jump, I think. But like in kind of terms of the theme, you'll see that we'll kind of come back to stuff that's not literally linked lists, but something that's like linked lists starting next week. With that said, well, you know, I think it's like not such a departure. So, all right. So let's talk about Fibonacci numbers again. So it's kind of a silly example, but I think it's kind of serves to illustrate a point here. So if you remember, if you implement the Fibonacci numbers without kind of any tricks, just with a recursive function, that takes O of 1.6 to the n. So it grows exponentially. 1.6 is pretty small, but 1.6 to the 100 is actually quite large, right? So even the 100th Fibonacci number is going to compute not very fast at all. So here's one approach to improving that. So first of all, the normal one, well, normal, I don't know, but we'll say if n is in 0, 1, we'll return 1. And otherwise, we'll return fib n minus 1 plus fib n minus 2. So like, as a refresher, this is literally what Fibonacci numbers are, right? It's like Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2. That's the definition. And we just plug the definition into Python. So if you remember, kind of the reason it's slow is that if you compute like Fibonacci of 10, it will repeatedly try to compute Fibonacci of 5, right? Because you call like, so 10 is kind of large, but you call like fib of 3, and fib of 3 calls fib of 2, and it also calls fib of 1. So fib of 1 returns right away, but fib of 2 calls fib of 1 again. And it also calls fib of 0. right? So here you see that if you call fib of 3, it calls fib of 1 twice. In general, you call fib of 10, it's going to call fib of 5 a lot of times, right? So one way to improve this is to say, well, how about we don't compute fib of 5 the second time that we need to compute it? How about we just remember every time when we computed fib of 5 already? So this technique is called memoization without the R. Right? So the way people would usually do it in Python is they would pass around this dictionary, which by default would be empty. And then just every time you compute something, you stick it in the dictionary. So we'll say basically if n is already in the dictionary, don't need to do anything. Just return fib data 10. If not, we'll compute it. And then we'll return it. So that's kind of the logic. So here you see that this is replicated. So this means that I could just move it here. And instead of this, I can say if it's not in the dictionary, then we compute it first. So it suggested autocomplete. Since you don't have the autocomplete, maybe I'll copy and paste it. All right. So this one you can also get rid of, right? Because you can just preload those into the dictionary. Comment it out. All right, so the structure is exactly the same. I'm still computing fib of n minus 1 plus fib of n minus 2, except I'm looking up whether fibdict has the value already, and if it does, I just return right away. So with this tree, it's not going to do anything for me. This tree is going to look exactly the same. But if you look one level below, so this is fib 4, and it calls fib 3, and it also calls fib 2. Well, this fib 2 is not going to call fib of 0 and fib of 1, because by this point, it already will have been computed, right? Because the way it works is, well, so yes. So in the code here, so fib 4 calls fib 3, and then fib 3 calls fib 2, and fib 2 calls fib 1, which returns. So you're here. And then fib 3 calls fib 1 again, which returns right away. And when fib 3 returns, we also record that Fibonacci of 3 is whatever it is. Right? And then fib 4, having gotten the output from fib 3, is now calling fib 2, which says, oh, I already know the answer. Right? So the tree is going to look like this. Fib 2 is not going to branch out. It already knows the answer. So what's the complexity here? Well, the easiest way to think about it is, well, you only compute every Fibonacci number at once. because the second time it's already been computed. There are n Fibonacci numbers. So kind of O of n. If you remember, there are issues with numbers that grow very fast, as Fibonacci numbers do. So in practice, that's going to be more. But in terms of how many additions, there are O of n additions. Yeah.
So what we know is algorithm that we've said, like, we want it to be faster, but also it's probably going to take up more space now.
Yes. That is a trade-off. Now, in this case, it's not much of a trade-off because there's just n numbers. The numbers also grow very fast. So that means that, like, I don't really want to formally analyze the space here, but kind of the intuition here is the numbers grow actually extremely fast, which means that the larger Fibonacci, like the last Fibonacci number, is going to take a substantial percentage of the space anyways. So in terms of the space complexity, it wouldn't actually matter as it happens. Yeah, well, I mean, it is a constraint. It's just that the last number is going to take up so much space that the fact that you need to store the smaller ones almost doesn't matter. But I don't really, well, like, why not? Let's do it formally. It's the hour after the linear algebra midterm. You deserve a treat. Whether people consider it to be a treat is a separate. So if you remember, Fibonacci of n is approximately phi to the n divided by square root of 5. That's like approximately the exact formula, right? So that means that the number of digits actually, I take it back. The last Fibonacci number is not going to take up like a large percentage. Is log fib of n, which is this, like, so n log phi minus a constant. Is everyone good with this? So this is log of this, which is n log phi, minus log of this, which is log 5 over 2. Does that make sense? So that means that the amount of space needed to store fib 1 through fib n is just log phi, which is a constant, times 1 plus 2 n. So the second term doesn't matter, it's just a constant, but Copilot wants it, so okay. Copilot has no idea what it's talking about. So this is O of n squared. Right? Just because 1 plus 2 plus 3 and so on plus n is n times n over 2. Over 2. And that is if we store in a list rather than the dictionary. So if you store it in a dictionary, then you actually need more, but we'll talk about that later. Yes.
What is phi?
pi is the golden ratio. So that's so this is like the analysis from ESC180. Make sense? So this is how much space we need, and this is a little bit of a, just like in an answer to a question. So I take back what I said before. In fact, yes, n digits, but just 1/n of the overall amount of space that you need. So yes, there is a trade-off there. So okay. And again, kind of this is a rough analysis. We're actually using a dictionary, which we'll see actually takes up more space than a list. And there really is a trade-off where, because the dictionary, well, not because, but for the same reason, the dictionary both takes up more space and is faster to access. Although in this case, wasn't necessary. So, okay. So the time complexity, though, is O of n, right? And that's because every Fibonacci number is computed once. And there is n of them. Right? So that's kind of like the quick way of figuring it out. The not so quick one is to say, okay, like this is what the tree looks like. And here it looks like a lot, like more than 4 cols. But actually, like if you think about it, what's going to happen is if you add Fib 5, here you'll again have a col to Fib 3, but that's going to be the last col in this branch, in the same way that this is the last col in this branch, and this is the last col in this branch. Because you will have computed 4 and 3 and 2 as you go from here to here to here to here, and then you never have to compute them again. So the shape of the tree here, so that's like a little bit more intricate than what we're used to. Right? Because so we're saying this is the full branch going to the left. So 5 to 4 to 3 to 2 to 1. So there is n of those. If you start with 5, there is n of those going over here. And then every time you make just one col going to the right. So 2n. Is that making sense? Questions? So again, if we're counting number of additions, the complexity is just O of n additions. If we're counting operations, need to account for the fact that addition takes O of k time, where k is number of digits. It's like not the in the larger number, sure. So I don't want to do it now. It's a similar calculation to what we had done with the space. Is that making sense? Questions? All right. Okay. So that's like this. So again, just to summarize, so this is like another version of what you can do. So on this slide, I just called so the reason it's called memoization is that the dictionary, usually it's a dictionary in which you record the numbers that you've already computed. It's called the memo kind of data structure, whatever it is. In this case, the dictionary. So that's why this is mem, and you can do it like that. That's the same thing that you've done before. So this is just a summary of what we've done. If people have questions, happy to answer. But I think actually like the presentation without the slide was better. So here is another approach that's actually quite similar in this case, and that is what's called dynamic programming. So programming in dynamic programming actually refers to an older sense of programming, which meant optimization. So if you, some of you will have an elective that's called linear programming, and that's really linear optimization. So it's just like an older term for optimization, like optimization in the sense of like, in the calculus sense of like, set the derivative to 0, find the critical points with that. All right. Here, of course, nothing is differentiable, so don't worry about that. So no derivatives, but we're in general, this technique would be used for optimization. In this case, it's kind of like the most general form of dynamic programming, which does not actually involve any optimization. So, okay. So the general dynamic programming approach is solve subproblems. So break up your problem into subproblems somehow, solve the subproblems, and then combine the solutions to the small problems to compute solutions to the larger subproblem, to the larger problems. And you can conceive of doing it with Fibonacci. So you could say, I'm doing kind of like memoization, but instead of doing it with a recursive structure, what I'll do is, well, first I'll compute fib of 0, and then I'll compute fib of 1. And once I've computed fib of 0 and fib of 1, now I can compute fib of 2. And now that I have fib of 2 and fib of 1, I can compute fib of 3, and so on. So the subproblems here are fib of 0, fib of 1, fib of 2. The big problem is fib of n. And what we're doing is we're solving the smaller problems first, and we're building up the solution to a larger problem. Right? So this is like nothing. This is like, well, I mean, technically we've done the complicated stuff in the ESC190 also, but like this is just in a way a weird superstructure right now on top of what should be kind of obvious, right? We have this list where eventually we'll store the solutions, and what we're doing there is we're just saying, like, I'll compute fib of 0, fib of 1, fib of 2, and so on, right? So that should make sense, right? Okay, unless like linear algebra fried your brain, it should be fine. So okay. So with that said, kind of even granting that this is maybe just overcomplicating what is kind of obvious, here is how you would think about it. So the complex problem is you have, in this case, n plus 1 problems. The ith problem is the ith Fibonacci number. You define the relationship between solutions to the more complex problems in terms of the simpler problems. The relationship here being the definition of the Fibonacci numbers. So fi is fi minus 1 plus fi minus 2. Store solutions to each subproblem. So in this case, in fiblist, and then use the store solution to solve the original problem. In this case, look up the value in fiblist n minus 1. So, okay. So that was kind of the prep. Here comes the difficult one. So here's a problem. So we have and like it's still kind of a more artificial problem than arranging your midterm schedule, but I think you will kind of see the relationship between this problem and that one as well. So we have a row of houses which we want to paint. Clearly this problem, people came up with it before the real estate crisis. So a whole row of houses and you own all of them, you want to paint. So okay, maybe you're the housing association. So for each house, we have a cost to paint it a particular color. So for example, to paint this color red would cost you 7. And to paint this house green would cost you 3, and so on. Maybe it's because, you know, like you need to bribe the homeowner to color the house in a particular color. I don't know. Okay. And like different homeowners have different preferences. And your rule is that you cannot paint 2 adjacent houses the same color, right? So if that weren't a rule, then the problem would be really easy. You would just say, well, just like, you know, this one is going to be red, and this one is going to be red, and this one is going to be blue, and this one is going to be blue because those are like the cheapest. But you're not allowed to paint 2 houses the same color. So that should kind of like call back, like you're not allowed to have 2 midterms on the same week or something. So like you can't have 2, like what did you have other than linear algebra? I forgot. So like whatever you had on Tuesday. So like you're not allowed to have like 2 subjects be painted with the same week or something. Not feasible in exciting. Yeah. So all right. So here you have an actual solution. So this is actually the optimal solution, and it costs 34. You can see how that seems a quite difficult problem, right? So one possibility is you just try every possible coloring and you just throw away the ones which don't conform to the rule of no 2 adjacent houses get the same color. And then you look at what is the smallest one. How much would that cost to run? Well, how many possibilities are there for painting the houses? It's 3 to the power of 6 in this case, right? Because 3 options for each house, the same as generating a password of length 6 with, you know, 3 letters allowed, right? So 3 to the power of 6 is actually not a huge number. I don't know what it is. We can figure it out. Yeah, so totally feasible, but even still, you couldn't do it by hand this way. And if it's not 6, but rather 60, that's not feasible because there is this many possible paintings. Colorations, I don't know. Okay. So here's the dynamic programming approach. And that requires like some combination of experience and problem solving to come up with. This is like not computing Fibonacci numbers here. And this is like really a non-trivial step. It should not feel like what I'm saying now just follows from what I said previously. This is a creative step here if you're defining those subproblems. So the subproblems are, I'll define 3 functions. So R of I is the minimum cost to paint the first I houses, given that the ith house is definitely red, right? So, for example, R of 2 is saying, what is the cost to paint the first 2 houses, that's the smallest cost possible, given that the second house is red? So what's the answer here is, well, you definitely pay 6 here, and then you get to choose whether to paint the first one green or blue, so you'll just pick the cheaper option. So R of 2 is going to be 9. Right? G of 2 is the same, except you are forced to paint the second house green. So that would be 8. And what's G of 2? Well, it's the smaller of 8 plus 7 or 8 plus 16. So G of 2 is 15. And so on. And we also have B of I. All right. So now it turns out, and that's the power of dynamic programming, is that having defined those subproblems, you can now, in the same way that we had done with Fibonacci numbers, just compute R0, G0, B0, and then R1, G1, B1, and then R2, G2, B2, and eventually you'll have the solution. And that would be possible for 60 houses, which is not possible with just enumerating all the possibilities. So here's how. If you know all the G's, the R's, and the B's up to I minus 1, it turns out that it's easy to compute R of I, G of I, B of I. Why is that? Well, because let's say that you want to compute R of 4. Right? So R of 4, what does it mean? It means I want to compute how much would it cost me to paint houses 1 through 4, following the rules, given that the 4th house is definitely red. So how much would it cost? Well, I'm definitely paying the 8 to paint house number 4 red. And now I get to say, well, what's the cheapest option for me for everything else? Well, if I know how much it would cost me to paint the 3rd house blue plus everything else before it so that I follow the scheme, and I know how much it would cost me if I chose to paint it green, and I know how much it would cost me if I chose to paint it blue, I know the answer, right? So I would just say, what's R of I? Well, it's how much it costs me to paint the ith house red and nothing else. Plus, I get to choose. Do I paint the previous house green or I paint the previous house blue? And I know how much that would cost me in total because G of I minus 1, B of I minus 1, I've already computed. Right? So the important distinction here is the cost is what it cost me to paint the 1 house. But G of I minus 1 is how much would it cost me if I follow the rules and minimize my cost and also paint house I minus 1 green. Right? So if I definitely paint the house red, then my choices for I minus 1 are either green or blue. And GI minus 1 and BI minus 1 tell me how much that would cost me in total. So for that reason, R of I is the cost of the ith house being painted red, plus the smaller one of GI minus 1 and BI minus 1. And for the rest of them, it's the same. Make sense? Questions? So, okay, how does it help me? Well, if I want to know what's the smallest cost in total, and I have I houses in total, I'll just look at which one is the smallest of R of I, G of I, B of I, because R of I is the cost of painting all the houses and also painting the last house red. G of I the same, but painting the last house green and so on. And I only have the 3 choices. So cost of I, therefore, would give me the best cost that I can get by following the rule of no 2 adjacent houses the same color and painting all the houses. Make sense? So, all right. So how would I compute this? Well, I compute B of 0, G of 0, R of 0. So let's switch to the code. So that is in the slides. That is my other computers. So clearly we're coming back to it tomorrow anyways, but 2 more minutes. So what I've done here is I just set up the costs. So this is just copied from the slides, right? So I just arrange it as a list of lists. Don't take pictures, like it's literally the code from the slides. I suppose you can take a picture as well. So I then make my costs. So I'll call it the array, even though it's a list of lists. So that's just going to be a bunch of zeros initially. And this would be like the R and G and B. And then I start the computation. So how would the computation go? Well, so here, like it's 0 in Python, it's 1 here. So R of 1, G of 1, B of 1 are just literally the costs. And then you get to compute R2, G2, B2. And that's exactly what we do, right? So we set R of 1 to just the cost to paint the first house red, G of 1, the cost to paint it green, B of 1, the cost to paint it blue. And then we just keep computing R2, G2, B2, R3, G3, B3, according to the formula that we had on the slides. So that gives us the cost. So we just compute like the minimum of all of those. And that gives us the cost. Note that it gives us the cost. It doesn't actually give us how to do it. So that will have to be left for tomorrow. All right. Okay. I'll see you. Bye.